My name's Luke.
My name's Michael.
And today we're going to be talking about equivalent circuits. Spilled a bunch of Kool-Aid. Gross! So in today's lab we're going to be dealing with a circuit that looks like this. So here's the circuit that we're dealing with today. We have a 70 volt power supply, and then we have a dependent voltage source over here. We can actually figure out an equivalent circuit that will basically give us these two connections. Since this is a dependent source, we can just leave that as 4VO. So if we were going to draw our equivalent circuit, what it would actually look like. So basically, we want to transfer this circuit over to this circuit and be able to get one resistor and one power supply. What we can actually do to this circuit is apply Kirchhoff's loop law, if I can talk here. So if we know that V sub 0 is equal to 1I or just I, doing some algebra, we can get 7 is equal to 7I. So then if we plug this back into our equation for I, just doing some solving for an unknown and then back solving, -1 times I plus our equivalence is equal to 0, VTH equal to 6 volts. So if we notice that V sub 0 is equal to 1 volt, we can apply that loop law again. I1 is equal to 0.0025 amps. And we know that I1 is 0.0025 equals to 0.0035 or 0.35 milliamps, which is equal to 2.8576 volts over 285.7 ohms, roughly 21 milliamps. Then last but not least, we want to know the current. If we were to stick a 300 ohm resistor between A and B, have a current divider between these two resistors, gonna be 10.66 milliamps.
So to check our math, we built this circuit in XIXX. This is going to be our independent voltage source for 7 volts. This is our voltage dependent voltage source with the positive end for VO, the negative end for VO right here. Voltage across when they're not connected is 6 volts, which is what we predicted. Current across them when they are connected by a really small resistor, which allows us to actually measure it in XIXX, otherwise we couldn't. Gets us 21 milliamps, which is what was also expected. We put a 300 ohm resistor just to see how it would affect the current, and when we click on it, we get 10.24, which was the expected value for that as well.
What we actually have here is two power supplies. Up here we have a 7 volt power supply, and down here we have a -15 and a +15, which is hooked up corresponding to our circuit.
So we have our 7 volts coming in through here, and this is going to be our V2. Peels off and feeds into the positive pin. And then this is our original 1K ohm resistor, which goes off into a separate 2K and 1K. This is going to be our V2. And we have a positive 15 volts powering chip and a negative 15 volts going on.
What we ended up doing is hooking up our DMM measuring voltage, and we have V1 over here in our red wire. Original 7 volts over here hooked up with the black wire. And what we're getting for a voltage across the system is 5.79 volts. So this setup looks a little bit different, but this time we're measuring current. And our current across the entire system, we're actually going to get 16.35 milliamps. So there's a big difference between what we actually get for a simulation value and what we get in the real world when we actually build the circuit. Sometimes the resistors are a little bit off compared to their true value on paper, and doing some of the math, it's a pretty complicated equation. So what can actually happen, that little bit of difference can be magnified by quite a bit, so it can throw the numbers off just slightly. If we were to hook up a 300 ohm resistor, measures the current, we actually get 10.66. So the last thing we're going to do is we're going to measure the voltage across the 300 ohm resistor. And again, we get 5.78. So we hope you learned a little bit about equivalent circuits and difference amplifiers in this week's video. Thanks for watching, and we'll see you next week.